Hello and welcome back. In section 3.2, we have to work with function types and applications. So first we'll start with our friend the linear. So a linear function can be written in the form f of x is equal to m times x plus b. So it doesn't necessarily say that it always is started that way, that it will always be presented in that way and that way only if it's a linear function. It's just saying we have to have the ability to get it there. Anything that doesn't meet this definition is referred to as nonlinear. So we have linear functions and nonlinear functions. So we'll start with view functions. And we'll find the independent variable. Dependent variable. Linear or nonlinear, and the name, what type of function it is. So we'll start with p is worth 1 over the quantity q minus 8. Our independent variable q, dependent one, the one that's by itself, p. This one is nonlinear. I would not have the ability to get this to look like this. I have a variable in a denominator, so this is nonlinear. The variable in the denominator means this is rational. Let's see, then we have k of t. It's worth 2/3 of t minus 7. Our independent variable for this one would be t. Our dependent variable would be k of t. This one is linear. I use different letters on it, but I have something times my input and then plus some other number. That is linear, so its special name is just linear. Let's see, we'll play with n of x. X squared minus 4x plus 5. Independent variable for that one. I'm plugging in x's. I happen to be plugging them into a couple spots, but that's okay. Independent variable would be n of x. Nonlinear this time because of the second power. First time because of the variable in the denominator. So no, not linear. The x squared means this is quadratic. And you remember our fun with the quadratic equations that we solved in chapter 2. We're going to see some more of those, and we'll see even a new method coming up in this chapter. M of t, absolute of the difference of 7t and 5. Independent variable here is t. Dependent variable is m of t. Nonlinear this time because of the absolute value. And because of the absolute value also leads us into what the name is, absolute value. That is an absolute value function. And let's see, let's play with one more of these. We'll do r of x is the square root of the quantity x minus 7 plus 3. Independent variable here is x. Dependent variable r of x. not a linear. I cannot make it look like constant times input plus a constant. The reason I can't do that is because of this radical. So that is a radical equation. So now that we have the sort of names of the different function types, and I tried to sort of sprinkle their use a little bit into 3.1. We get into using some of those as mathematical models. Models are sort of trying to describe real-world applications. So this first example, the cost of removing X% of dust. So this is something that's done in environments where you're either doing biological research or manufacturing sensitive electronics, things like that. Anything where contaminants from the air could get involved in your work. You're trying to remove all the dust and all the particulates from the air. So cost of removing X% of dust from, we'll just say a room. We talked about what type of room that could be. And let's say it's given by f of x is, and I'm going to stick with the author's example here, 20x over the quantity 100 minus x. So this one is a rational function. The fact that we had a variable underneath the denominator is what told me that. If I just had a number in that denominator, this would have been considered linear. The fact that the variable is here tells me that this is a rational function. The independent variable in this one is x, and what it represents, percent of dust removed. Dependent variable would be f of x, cost, and we're going to assume in dollars unless otherwise stated. So cost in dollars. So we have control over how much we want to remove. Once we pick how much we want to remove, then we calculate the result of that, the dependent variable, which will give us the cost. And we'll take a look at what happens with 0, 20, 50, 95, and 100. So our rule for this model, f of x is 20x over the quantity 100 minus x. range, the cost, is our f of x and our ordered pair. So we'll start with f of 0, so 20 times 0 over 100. I'm going to have to scooch these down a little bit. 100 minus 0, so that's 0 over 100, which is 0. So 0, 0. So basically on this one, it costs nothing to remove none of the dust. Okay, makes sense. Now I'll put my 20 down there. So f of 20, 20 by 20 over 100 minus 20. So that's 400 divided by 80. So 40 over 8 is 5. And let's see. Oh, my apologies here. Our cost is in not dollars, but thousands of dollars. So if I get a range value of 5, that really is representing the idea of $5,000. So kicking 20% of the dust out of the room will cost us $5,000. Alright, so I'm going to ask you to run it through with the 50 and with the 95. And we'll do the 100 together. Go ahead and pause it and figure those out. Okay, welcome back. So f of 50, 20 by 50 over 100 minus 50. So that's 1,000 over 50. So 100 over 5 is 20. So 50 comma 20. So what that actually means, removing 50% of the dust would cost $20,000. F of 95, 20 by 95 over 100 minus 95. So 1,900 over 5, which is 380. So removing 95% of the dust in the room, now that's running us $380,000. The one that I put up here and mentioned we wanted to go through that together, f of 100, 20 by 100 divided by 100 minus 100, 2,000 divided by 0, undefined. So there is no ordered pair if we have something that is undefined. So according to the model, it's not possible to remove all of the dust, at least, again, according to the mathematical model. Now, another common thing we can do with this, though, instead of just plugging and chugging and getting an infinite list of values, sometimes the bosses are just going to come to you with a budget, and they'll tell you, for example, let's say you got $180,000 to remove dust. How much can we remove? So first off, remember our f of x was measured in thousands of dollars, so they're telling us that f of x here would be 180, and we understand it to be in thousands. So recalling the formula from the previous page, f of x was 20 times x over 100 minus x. So this time, instead of giving us the x, they've given us f of x. They gave us the other side of the equation. So 180 is worth 20x over 100 minus x. So we're solving for x, the amount of dust that we can remove. Okay, so we already have our domain restriction from earlier. X cannot equal 100. Because it's a percent of dust removed, I can't remove more dust than 100 anyway. More than 100%, I can't remove more dust than was already in there. So here our domain is even further restricted. We can't have negatives also. Otherwise, we would basically be blowing dust into the room. So back to our work with solving rational equations. Next up, we find our LCD for the problem, in this case 100 minus x. So we'll multiply both sides by 100 minus x. 100 minus x over 100 minus x is worth 1, since x is not worth 100. So 182, so 18,000 minus 180x is worth 20 times x. So then the addition property of equality up next. We'll add 180x to both sides. So 18,000 is worth 200 times x. Divide both sides by 200. So factor out 100 there. So 180 divided by 2 is 90. So with $180,000, we can remove 90% of the dust in the room. So you bring that to the folks that will be working in there, and hopefully that's within the tolerance level that they can use for, again, whatever we're working on, electronics, biology, etc. Now, one other nice application problem that we're going to explore, and this is another one of your authors, is the McDonald's problem. So the number of McDonald's a given year is modeled by, let's see, we have f of x, 16x squared minus 40 times x plus 300. And x is the number of years since 1960. So this is worldwide, the number of McDonald's. So first off, see if you can figure out what type of function is this. Hopefully you spotted that x squared. That would tell us this is quadratic. Independent variable, x represents the number of years since 1960. Dependent variable, number of McDonald's in the world, and our variable was f of x. Okay, so then we're going to look up we'll do the model first. How many McDonald's are there predicted? We don't need there. How many McDonald's are predicted to exist today based on the model? So we are in 2021, so we're talking 61 years since 1960. So we would find f of 61. So f of 61, 16 by 61 squared minus 40 times 61 plus 300. So f of 61, we then plug and chug in the calculator there. We get 57,396. So the predicted number of McDonald's is 57,396. Actual number of McDonald's, this I pulled on the web, as of 3/24/21. The actual number today is 38,695. We'll be generous and call them restaurants. So notice our model is pretty far off. The reason for that mathematical models are usually not precisely exactly what happens. They're a good way to approximate what will happen. The reason for this, this model, the given function is based off data from, let's see, where was it, 1955 through 1987. So I would be very comfortable using this model to predict the number of McDonald's restaurants in 1988. 1989, maybe even as far as, maybe out as far as 1995 or so, because we have such a huge range of years. 1987 to 2021, though, not comfortable with that at all. You want to stay close to your data set, and in your stats class, those of you that are going the 126 route, you'll talk about that in a lot more detail. Those of you taking 115 may touch on some stats as well, but you do want to stay close to your original data set. That's the reason that this is off. All right, so the problems that I would recommend trying, the 3.2 exercises, and there's also a project number 7 in the back of the book. That gives you a really nice model to sort of run through a similar problem to what you're going to be asked about on quizzes and tests and other projects and things like that. So try both of those, the 3.2 exercises as well as project number 7 in the back of the book. As always, if you have questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.